Hi, and welcome to this video on the center of mass. In this video, you will learn what the center of mass is, why it is useful, and how you can apply it to everyday problems, including ones on balance. We will then look at how this center of mass, or COM for short, alternates during walking and why this is important. Let's start off with the definition of the center of mass. As the name implies, it is the central, average, three-dimensional point of the relative mass of an object. Let's look at this example. You see a square with its weight equally distributed over its area. This means that the center of mass is right in the middle of the square. Now let's look at some other shapes. In these images, you see several shapes. Can you guess where the center of mass is located? As you might have guessed, for these shapes, the center of mass is positioned in the middle, just like for the square. This seems simple, but it can easily get more complicated when the shape gets more complex. For example, an exoskeleton is way more complex than a square. It has a more complicated shape, consisting of many different parts with all different types of shapes and sizes. Additionally, the weight in these parts is not uniformly distributed. Let's look at what that means. With a square, you can assume that the weight is uniformly distributed throughout the object. Each part of the square should have the same density and thus the same mass. For an exoskeleton, however, some parts are more dense than others and are thus heavier. This means that the center of mass is not positioned in the middle and that it is more difficult to calculate where it is positioned. Fortunately for us, a computer can still calculate this. However, even for a computer, this becomes more difficult when the center of mass alternates during walking, and the pilot makes unpredictable movements that influence the center of mass. Before we get into calculating the center of mass, let's first look at its usefulness. And let me ask you a question. Have you ever tried to balance a piece of paper on your finger? If you have, you probably noticed that it is easy to do. You find the middle of the paper and it stays balanced. This is because the center of mass of a piece of paper is also in the middle, like we saw with the square. More generally, if you were to balance an object on your finger, placing your finger under the center of mass of an object would be the way to do it. This doesn't always work in practice though. Just look at this shape. While in theory, you can balance the shape by using the center of mass, in practice, it will be very difficult to do so because you can't place your finger there. Still, the center of mass is very useful in calculations. It allows you to reduce an object to a single point, called a point mass. And with this point mass, you can carry out all kinds of calculations. Let's see how you would normally calculate the center of mass using this broom as an example. Looking at it, we can say that it looks a bit like the letter T. Now, if you want to balance this broom on your finger, where would you place your finger? You probably wouldn't place your finger at the exact middle of the broom. It would tip over. This is because the mass of the broom is heavier at the side of the broom head than on the opposite side, causing the center of mass to move more towards the broom head. In physics terms, it means that the weight of the broom is not uniformly distributed throughout the object. So, it's obviously important to take the weight distribution into consideration when trying to find the center of mass. So, in the beginning of the video, we saw that it was easy to find the center of mass for simple shapes, such as a square. And as we also saw, it is more difficult to do so with a broom, because we concluded that the weight distribution, or density, is an important part of the center of mass. If we create a set of axes, we'll get the following. What happens when we use the broom from earlier? As we said, it kind of looks like a letter T, but unlike the square, it doesn't have a uniform density. So we can divide the broom into two parts, the stick and the head. Let's assume that both the stick and the head do have a uniform density individually. If we want to find the center of mass of the whole thing, we use the following formula. COMx stands for the center of mass for the x-coordinate and COMy for the y-coordinate. The m is the mass of the object and the x or y is the coordinate of the object. Simply put, you multiply the weight of different parts with their individual center of mass, add these up, and then divide by the total mass. If we fill in the numbers for the broom, we get the following. Let's see what that gives us. So now we know that if you want to balance the broom on your finger, you should place the finger near the head of the broom at the coordinates 2 and 2.55. This is our point mass, which we can use in other calculations, or use it to balance the broom on our finger. While we did this for a two-dimensional object with only an x and a y coordinate, it can also be done for a three-dimensional object. Next to the COMx and COMy, you add the COMz to the equation. This gives you a 3D point mass with an x, y, and z coordinate. It can even be done for an exoskeleton, although that will be too complicated to do by ourselves in this video. In a real-world dynamic situation, the center of mass can be more difficult to work with. For a broom, the center of mass never changes. But when you're walking, your center of mass is constantly changing as you step from left to right. You can see a change on this image, where the center of mass goes up and down while you take a step. Your body is well equipped to keep your body balanced despite a changing center of mass, but this is more difficult to do with robots and exoskeletons. While robots such as Boston Dynamics' Atlas actively use their own center of mass to stay balanced, similar results have not yet been achieved for exoskeletons. The main reason being that the presence of a human makes it a lot more difficult to accurately calculate the center of mass over a longer period of time. You'll learn more about this in the upcoming reading material.